Hello, ladies and gentlemen. Today we're going to talk about the comparison between the alternative current motor and the brushless direct current motor. We will also talk about which one is better or more widely used by, people in everyday lives. Now, before we dive deeper into the subject, allow me to introduce myself. My name is Iklas. I am from Group B618. Here are my teammates. This is Chu. What's up, Chu?
Hi there, E-Class.
All right, and that's Abuza. How you doing there, brother?
Doing great, my friend.
All right, I think that's enough with the introductions. Let's get into it. The direct current, or DC, works in a way that the electricity charge flowing through a certain circuit is in one direction, while alternating current, or AC, means that the charge flow changes over time. Now, these currents are usually used to drive electrical motor. What is a motor, you say? Well, a motor is an electrical machine that converts electrical energy into mechanical or kinetic energy. Now, there are many types of electrical motors. For DC, we have multiple examples such as the electromagnetic DC motor, DC motor, brushless DC motor, and so much more. But just for today, we're going to focus on the DC motor only. Alright, so before we learn about the brushless DC motor, we have to know a little bit about the brush DC motor first. Now, I know I said that we were going to focus on the brushless DC motor, but trust me, this will help you to understand better. Alright, a brush DC motor has permanent magnets on the outside of its structure with a spinning armature on the inside. The permanent magnets, which are stationary on the outside, are called the stator. The armature, which rotates and contains an electromagnet, is called the rotor. In a brush DC motor, the rotor spins 180 degrees when electric current is run to the armature. To go any further, the poles of the electromagnet must flip. The brushes, as the rotor spins, makes contact with the stator, flipping the magnetic field and allowing the rotor to spin a full 360 degrees. You got that? Alright, now we're gonna go into the brushless DC motor, or the BLDC motor for short. Well, a BLDC motor is essentially flip inside out. It eliminates the need for brushes to flip the electromagnetic field. In a BLDC motor, the permanent magnets are on the rotor and the electromagnets are on the stator. A computer then charges the electromagnets in the stator to rotate the rotor a full 360 degrees. So next, let's learn a little bit on how to control a BLDC motor. So of course, we have a control unit, and this may be implemented using several high-tech choices, such as a microcontroller, a hardwired microelectronic unit, maybe a programmable logic controller, or PLC for short, or any other similar units. The BLDC motor is a very popular component and is widely used and applied in a lot of fields, such as using, consumer electronics to make phones and laptops, in transports, heating and ventilation systems, industrial engineering, and even model engineering. So yeah, that's it for BLDC motors. And now I'm going to pass it over to Abuzar. So yeah, thanks for hearing. Take it over, Abuzar.
Alright, now allow me to explain more about AC motor. The conversion from alternating current into mechanical power by using an electromagnetic induction phenomenon is called an AC motor. This motor is driven by an alternating current. The stator and also the rotor are the two main important parts of AC motors. The stator is the stationary part of the motor and the rotor is the rotating part of the motor. The AC motor may be single phase or three phase. There are two main types of AC motor. First is the synchronous motor and the other one is induction motor. Okay, let's talk about synchronous motor. Synchronous motor is a motor which runs at a synchronous speed. The synchronous speed is the constant speed at which motor generates the electromotive force. The synchronous motor is used for converting the electrical energy into mechanical energy. The stator and also the rotor are the two main parts of the synchronous motor. The stator becomes stationary and it carries the armature winding of the motor. The armature winding is the main winding because of which the EMF induces in the motor. The rotator carries the field windings. The main field flux induces in the rotor. The synchronous motor uses the salient pole rotor. The word salient means the poles of the rotor projected towards the armature windings. The rotor of the synchronous motor is made with the lamination of steel. The lamination reduces the eddy current loss occurs on the winding of the transformer. The salient pole rotor is mostly used for designing the medium and low speed motor. For obtaining the high speed, cylindrical rotor is used in the motor. Next, allow me to explain how synchronous motor works. The stator and rotor both are excited separately. The excitation is the process of inducing magnetic field on the parts of the motor with the help of electrical current. When the three-phase supply is given to the stator, the rotating magnetic field developed between the stator and rotor gap. The field having moving polarities is known as the rotating magnetic field. The rotating magnetic field develops only in polyphase system. Because of the rotating magnetic field, the north and south poles develop on the stator. The AC is sinusoidal. The polarity of the wave changes in every half cycle. When the rotor and stator both have the same pole on the same side, they repel each other. If they have opposite poles, they attract each other. Furthermore, the rotor attracts towards the pole of the stator for the first half cycle of the supply and repulses for the second half cycle. Thus, the motor becomes pulsated at only one place. This is the reason because of which the synchronous motor is not self-starting. Now, let's talk about induction motors. Induction motors are referred to as synchronous motors or rotating transformers. This type of AC motor uses electromagnetic induction to power the rotating device, which is usually the shaft. The rotor in induction AC motor products typically turns slower than the frequency that is applied to it. Induced current is what causes the magnetic field that envelops the rotor of these motors. This induction AC motor is designed in one or three phases. Next, let's talk about how induction motor works. The fundamental operation of an AC motor relies on the principle of magnetism. The simple AC motor contains a coil of wire and two fixed magnets surrounding a shaft. When an electrical or AC charge is applied to the coil of wire, it becomes an electromagnet, generating a magnetic field. Simply described, when the magnets interact, the shaft and the coil of wire begins to rotate, operating the motor. In an induction machine, the armature windings serve as both the armature and field windings. When the stator windings are connected to the AC apply, flux is produced in the air gap. The flux rotates at a fixed speed called synchronous speeds. This rotating flux induces voltage in stator and rotor winding. If the rotor circuit is closed, the current flows through the rotor winding and react with the rotating flux, and a torque is produced. In a steady state, the rotor rotates at the speed very close to synchronous speed. Okay, moving on. There are a lot of applications of AC motors in our daily lives. As in the slide, we can see the examples of application classified according to the types of AC motors. Next, let's look at the AC controller that we normally use to control AC motor, which is the variable frequency drive or VFD. The VFD is a particular kind of adjustable speed drive that is used to control the speed of an AC motor. In order to control the motor's rotational speed, a VFD controls the frequency of the electrical power supplied to it. Adding a VFD to an application allows the motor speed to be adjusted in accordance with the motor's load, ultimately saving energy. Commonly used in various applications, a VFD can be found operating in ventilation systems, pumps, conveyors, and machine tool drives. The three main common VFD designs includes current source inverter CSI, voltage source inverter VSI, and pulse width modulation PWM. Okay, for the last part, let's see how a VFD works. When complete voltage is applied to an AC motor, it accelerates the load and drops torque initially, keeping current especially high until the motor reaches full speed. A VFD operates differently. It eliminates excessive current, increasing voltage and frequency in a controlled manner as the motor starts. This allows the AC motor to generate up to 150% of its rated torque, which could potentially be generated from the beginning all the way up to full speed without wasting energy. A VFD converts power through three different stages. First, AC power is converted to DC power, followed by the switching on and off the power transistors, causing a voltage waveform at the desired frequency. This waveform then adjusts output voltage according to the preferred designated value. And the advantages of using VFD can also be seen in this video.
Thank you, Abuza, for such a detailed explanation. Now, I believe that my teammates have told you everything you need to know about the brushless DC motor and also the AC motor. So my job, as you might have guessed, is to compare and contrast these two types of motor. First, let's talk about similarities. Since we have narrowed down the DC motor to the brushless type, we know that both types of motor that we are comparing here do not use brushes in their construction. This means that in terms of maintenance and friction or sparking caused by the brushes, we are at an equal playing field. Next, we also know that both motors run on the principle of magnetism, either using electrically induced magnet or permanent ones. The basic purpose of the two motors are also the same, which is to generate mechanical energy from electrical energy. Now let's talk differences. In terms of efficiency, the brushless DC motor prevails. An AC motor experiences energy loss when energizing the electromagnet needed to make it work. On the other hand, the brushless DC motor uses permanent magnet, which obviously does not consume extra energy from the electrical power supply. The controller on an AC motor is called the variable frequency drive, or VFD for short. On a brushless DC motor, it is the Hall effect sensor. As you can already see from the picture, the VFD is quite bulky and controls the motor's speed by changing the frequency. The Hall effect sensor is clearly the winner here, as it is much more compact, yet provides precise data up to the point where it can be used to align the rotor and stator of the brushless DC motor. The small size also means that it can be easily fitted into a circuit board and allow more functions and full control over the motor's speed, torque, and acceleration. At high-speed operation, the winner is yet again the brushless DC motor. Due to the way an AC motor energizes the electromagnet to work, and also the controller used to control the speed, an AC motor loses torque as it speeds up, because remember, it cannot control the torque and speed at the same time. So the increase in speed leads to a decrease in torque. The brushless DC system provides a flat torque over a wide speed range since the Hall effect sensor is so precise, and also the usage of permanent magnets eliminates loss of energy. Some companies, such as Oriental Motors, even has several brushless DC motors packages offering speed control from as low as 3 RPM up to as high as 4000 RPM. With all that being said, however, AC motors are not completely useless. Applications that do not require speed control and some other specific applications are better off with AC motors. This is because AC motors that does not need to control the speed won't be needing a VFD, due to the fact that it can run on the AC current alone as the frequency is already varying. This makes it more cost-effective to use an AC motor in such applications. In a nutshell, the motor that is better, most of the time anyway, is the brushless DC motor. This is concluded based on its ability to have full control over the motor's speed, torque, and acceleration, its efficiency, and its high-speed operation capability. The motor that is more widely used is, of course, the brushless DC motor. This is because it is capable of many applications and also because of the fact that most applications require the speed control that only a brushless DC motor can provide as opposed to an AC motor. The more cost-effective option when it comes to certain applications is the AC motor. In applications that do not require speed control, the controller can be omitted from an AC motor and it can run directly from the AC current source.